Lecture 8. It's the continuation of the topic Data in GIS, Acquisition and Input. These are the topics being covered in this Lecture 8. We're going to look at some of the data acquisition methods in terms of field survey methods, the digitizing of maps, photogrammetric methods, remote sensing, and image processing methods that we use in order to get the data in the format that we want to use in our application. We also look a bit about the GIS data types, and the different types as listed there. One of the common method of acquiring data is field survey methods. This is typically done if you're looking at getting property boundaries or setting out roads or doing anything that requires collecting the data and then presenting it out in the field. You're talking about a licensed land surveyor or someone who's competent enough to learn, well, to use the surveying equipment that we have nowadays. Now, survey methods is varied. Long ago, in order to position points on the Earth's surface, when I say position, in order to get the coordinates of points which we can use as control on the Earth's surface, to get the coordinates of them, it was traditionally done using what we call triangulation. Triangulation is establishing a set of ground control points by using observed angles of triangles that represents the landform. So you'll have a set of intervisible points on the ground, and you would go out in the field and set up your total station or theodolite or transit and measure angles between indivisible points. And you measure all of these angles, and then together with one distance that is measured, using a set of mathematical models, the control points of all the points that are observed will be calculated in terms of the coordinates for them. So you're going to get X, Y, and Z values for each of the control points that are intervisible. Another common method still being used is traversing. It's propagating ground control using existing control points. Alright, traversing is one of the common methods the licensed land surveyor would adopt in order to get secondary control points within the study area that is being collected in terms of the data that's required. Another field method is leveling. It's propagating the height information on the ground. Now, each control point that you would get that is documented online and also available, if available, on the ground, they would tell you on the monument on the ground of the point whether or not if it's a horizontal control or vertical control. Horizontal meaning it will tell you the X and Y. There's an accurate determination of the X and Y location. Vertical control, there is an accurate determination of the height or Z value. Another common field survey method is global positional system using commonly known as GPS, where we would use GPS and cores network and go out in the field with less equipment compared to what a traditional land survey would have used, and get X, Y, and Z values of points of interest. This is commonly being used nowadays when collecting data out in the field. Tachyometric survey is a British term that is used to refer to as-built surveys. It entails picking up details from existing control points in order to prepare topographic maps an engineering map. So I can set up a total station or theodolite on a control point, and then start collecting the coordinates for where the buildings are, the various dimensions of the building, and be able to download that later on when you get back into the office, into your GIS. Other survey methods depend upon the data types. Example, the common survey methods, non-survey methods, is doing census surveys, going out there and getting how many people living in a house, average income, number of kids, things like that. All data output are in X and Y data format, except the last one, which is identified, which is in a tabular form. On this slide, it shows you the three of the methods that use to establish ground control of points on the Earth's surface. The first method is triangulation. As I said before, triangulation is determining ground control of points. If I know this point and the other points are indivisible, I will go out in the field and measure only angles. So I'll set up the total station to observe the angle between all of these triangles. Then I'll go to the other location, which is a long distance away, but they're indivisible, and set up and measure these internal angles. Do it for all of these points, and using trigonometry and computer program with one known baseline, all the other points, ground control points, are determined. Now, the other method, which is the reverse to triangulation, is called trilateration. And instead of measuring internal angles, what they do is actually measure the bearing of a particular line. All right. So in this case here, they're measuring the azimuth of this line here using that angle. It's well determined, and they measure only distances of all of the lines that are indivisible. They will determine what are all of these distances between the points using computational methods and computer program. They are able to determine what are the ground control of the points that are indivisible. The other method is what we call traverse, which is more commonly used by licensed land surveyors. They will use azimuth of a particular line, and from the azimuth they can determine what is the bearing and distance of this particular line by making observations, angular observations, and also distance measurement. They can compute what is the coordinate of this location, the other location, until they reach a known location, a known point. On this slide, I just wanted to show you how big a distance, in terms of how long a distance the points are. In the background, you see an imagery of a certain area on the Earth's surface, but if you look at this line here, it's a long distance away from one point to the other. This is the top of the mountain. The known distance they would have measured was this distance. Okay, so triangulation we are looking at here, and what they did was actually set up the total station and measure these internal angles, and go and measure each one of them. Again, same thing what I explained before. This is what traversing is about. Using your total station and indivisible points. This is a known point, this is a known point, and using the azimuth of a particular point or the bearing between 2 points, one was able to coordinate what are the coordinates for this point, this point, and this point. And that's what the licensed land surveyor would do. So this is an example for traverse where they determine the coordinates of other points based upon some known points, by determining the bearing and the distances. So this is, and again, they use trigonometry to come up with these coordinates. The other method is leveling. What you see here is that at this location, position 1, using a graduated staff that has measurements in terms of distances from the ground. So at the base of the rod is 0, 0, and as you go up it increases in the distance. And using my automatic level, I can read off the height of the rod wherever it's placed. If I know the location of one of these points, then I'll be able to determine what is the height of point A, what is the height of this location here, this C, D, etc. Okay, and this is what we call differential leveling. Surveyors and licensed land surveyors and civil engineers would use this method to get heights of points, and ultimately, when you talk about heights, it's with respect to mean sea level. Other method is global positional systems, is commonly used. Just to explain a bit about it, is we have a set of GPS satellite orbiting the Earth's surface. So we have a number of satellites orbiting the Earth's surface. It is continuously monitored by a set of receivers, continuous operating system, cores, network, and the user can be a licensed land surveyor or civil engineer who understands how to use a GPS. He can buy a receiver and just get the corrections from the cores network, also getting the signals from the satellite, and he's able, using the receiver, to determine his position. What you're seeing here is the end user who has a GPS. This is the GPS receiver and his data collector, and he's actually getting the X, Y, and Z value of that point on the ground. Very common method. It's a common method being used by a lot of the professionals out there. This is an example of an as-built survey. So the method used here is using they could use GPS, actually they could use also total stations, but the product is they would go out in the field, collect the location of where features are, in this case, and then come back into the office and draw the map to a particular scale. In this case here you see the roadway, and you also see the details of the concrete driveway was picked up, and the house is two-story house, and the property boundaries. This is an idea. This is an example of an as-built or survey, or in some countries, like in UK, they refer to it as tachyometric survey. In addition to the legend, you have your note arrow. You also have more information: survey notes, surveyor's certification. This is where he's going to sign and put his stamp. And other zone information. It gives it scale, the lot number, and also the company information. Another method of acquiring data is digitizing existing maps. We talked about manual digitizing, where we collected vector data and its coordinated data points as stored in the database. We talked about before scan digitizing, where a scanner is used and pixel information is stored and raster data. Another method of digitizing is what we call on-screen digitizing. It's a semi-automatic method which makes use of line following capabilities software that does these things. So you can, for example, have an imagery in the background on the computer monitor, and you would be tracing out features that you would see on the area, on the image, and you're actually creating data sets that you didn't have before. When you do on-screen digitizing, you are collecting vector data, which is coordinate data. For the last two methods, it is required that color separates be used for color mapping. So what we're saying is that if you're going to do on scan digitizing, it's recommended that you get the original separates that was used to create or produce the topographic map. Why? Because if I have to scan the entire topographic map, the scanner will capture everything on one image. Alright, so it's going to capture table of the legends, the north arrow, all of the text, all of the lines, all of the features on the map, and you're gonna spend a lot of time extracting the features into separate layers. So I'm going to want to have the roads on one layer, I'm going to want to have the vegetation on one layer, and I'm going to want to have the buildings on one layer. So there's a lot of post-processing. Even the post-processing of a scan image, even though it's much faster, the post-processing procedures is much more demanding. Scan data need conversion into coordinate information and requires the coding for GIS input. Involves rasterization and vectorization process. Rasterization is if I take a vector data, which is coordinate data, and convert it to raster, that process is called rasterization. And the reverse to that is coordinate data, which is vector data, convert that to raster is rasterization. The reverse to that, raster data to vector data, that is vectorization. There are various inaccuracies that are involved in the conversion, and it all depends. It all depends what resources are available, the budget, and also the time available for the project. There's always the need for a check plot, which will be used to overlay in the final result. So whatever I do, if I do rasterization or vectorization, make sure there's some way of checking the accuracies. Here you see an example of a digitizer board, a little diagram of it. This board can vary to your, it varies in size, very small in size, to even to A0 size digitizing board. You would have a sensitized area on the board. You also have a digitizer puck that has a crosshair. That crosshair indicates the data you're going to capture. Once you put the crosshair over that particular point and you press the button on the digitizer puck, that coordinate is transferred electronically and stored digitally in a computer. You would put your map on the surface. You would have your ground control on your map. You would have the X, Y, Z values of ground control on the map, and you would transfer or do a transformation. The system would do the software would do a transformation from your digitizer coordinate system to your ground coordinate system. So anywhere you move that digitizer mouse, you would actually see it moving on the monitor. Here you see an example of a user digitizing a map, and the digitizing table here, as you can see, is relatively big, larger than the guy. Alright, so he would secure the map properly with masking tape, make sure it doesn't move, put in the ground control, and using software like AutoCAD, ArcGIS, or any other GIS software, do a transformation from your digitizer coordinate system to your ground coordinate system. Here are two examples of scan digitizing. This is a high-end scanner, huge. You're going to put your map there properly fastened, and then the scanner is going to scan. You can have more than one map in this scanner, and it will scan all of it, store it digitally in the computer on the hard drive. Here is compared to this one here, it's a low end, but it's very good. It has its own software attached to the scanner, and it will scan one map at a time. This is an example of on-screen digitizing. This guy here, he has a imagery in the background using a particular software, and he created some layers, and based upon those empty layers, he would start tracing out the features that he would see on the images. Now, please note that your images is not an image that you would get from your camera. It has to be an ortho-rectified image, which means that the image the effect of some errors associated with imagery has been reduced, and also the image would have a defined coordinate system. So once you have an orthorectified image, you can get that from satellite imagery or aerial photographs. You would add that imagery in a computer environment using a software and start digitizing the features that you would see. Which one is better? Is it scanning or manual digitizing? Answer to that, which one is better? Neither. Note, please. Why I say neither? Because it all depends upon the application. It all depends upon the application. If I'm looking at satellite imagery, obviously I'm looking at scanning my data in. These are some comparisons of scanning versus manual digitizing. Scanners are more expensive than digitizers. Scanning needs more sophisticated software, while all GIS software includes some form of manual digitizing capability. There are more steps in scanning process, post-processing steps that I'm referring to. Scanning requires less highly trained personnel. So to do a scan, basically set it up on the scanner, make sure it's within the area that is sensitive to the scanner, and just press start and it'll scan. That's it, doesn't take a lot. Scanning process is 50 to 10 times faster than digitizing. That is true. The after process of scanning, it's much faster than manual digitizing. Scanning works best with maps that are clean, simple, and do not contain extraneous information such as text or graphic symbols. Yes, that's what I'm saying before. If you have the original separates that was used to create your topographic map, you can scan those separates, and it'll be easier for you to, less work for you to put those different features on different layers. Scanning is most cost effective for maps with a large number of regular shaped features, example contour lines, and that is true. If I have, it's difficult to actually digitize follow contour lines, especially if the contour interval is very small, like 1 foot. It's very difficult, and especially another consideration is if you have more than one map. Manual digitizing is more cost effective when there are relatively few, while maps that have a lot of extraneous information requires interpretation. So this comparison just to identify the pros and cons of them, and of course if you are asked which one is better, it will always, your response to that, it depends upon the application and the resources that you have. Another method used of acquiring data is your photogrammetric methods, and there are two types, the conventional and the analytical method. Conventional involves the use of large stereo plotters, where aerial photographs are used on equipment called stereo plotters that reconstruct the position of the aerial cameras at the time the photograph was taken when it was in flight in the airplane. The output is a hard copy map which requires conversion into digital format. So it's an analog form, all right? And we don't use these stereo plotters again, the conventional one, the analog one. It will take the overlap areas of sequential photograph and create 3D models and introduce the ground control, and where we can digitize the features from the 3D models. The other method, more popular method in photogrammetry, is called the analytical, and it involves the use of computer hardware and also this photogrammetric software, which are used to reconstruct the position of aerial camera at the time of photography. It uses computer models to create a 3D model, and it's much faster, more accurate, and you can digitize very easily in 3D, capturing vector data. On this slide, you see an example of one of the traditional photographic methods. It's an analog stereo plotter. It's a huge equipment. What the guy is doing there, he's actually viewing the 3D model that he would have had followed a particular procedure to create that 3D model. And as he moves his hands in the Y and X direction, he would be seeing a floating mark in his eyes, looking at the 3D image, and using a thumb wheel at the base, using a thumb wheel on that particular type of mouse, he can change the height also in order to measure the particular feature he wants to measure, in order to capture the X, Y, and Z values. Now, the analog stereo plotters are not being used nowadays because they're too bulky and it's not as accurate as our digital copies, our digital analytical stereo plotter. This is an example of our analytical stereo plotters. It is much more versatile in terms of its ability to create 3D models much faster, easier to use, and it also comes with a number of software that would help in creating these 3D models accurately and faster. What you're seeing here is that this user is actually one screen. She has the 3D model using specific stereo glasses that will help her to see 3D. And on this other monitor, she has the CAD system where, as she draws particular features from that 3D model, she will be seeing the CAD drawing as she draw the features from it. Alright, so here is 3D, and here you will get a CAD drawing being displayed. The other method of acquiring data for your GIS, called remote sensing and image processing. Note that photogrammetry that we spoke about before in previous slide is one method of remote sensing. Now, in this method I'm shown on this slide, remote sensing is in particular reference to the imagery obtained from satellites. It involves the use of satellites which record the energies emitted and reflected from the Earth's surface. The resultant image recorded needs to be processed in order to address a number of corrections. Satellites that orbit the Earth's surface will be capturing small scale, meaning the spherical nature of the Earth's surface will come into play, and larger areas being covered and at a very far distance from the Earth's surface. So there will be some inaccuracies, and there will be the need for some post-processing to address these inaccuracies. You need to apply a number of corrections. For example, I've just listed them out here. Radiometric corrections is the removal of haze corrections due to the variation in weather condition. Removal of cloud cover, things like that. Geometric correction applies the spherical nature of the Earth's surface, be able to address the spherical nature in the final imagery. Image enhancement, if I want to smooth out my image, get a better view of the image, I can do some image enhancement, or I can do some image classification. We have supervised and unsupervised classification, where I would extract the pixels that I'm interested in, or that is a supervised classification. I will tell the system, select for me pixels 10 to 20, that's vegetation, 20 to 30, that's urban areas, etc. Or I can just leave it for the computer to do an unsupervised classification, where it will, the software in the computer would define the ranges and come up with these classes. The remote sensing and image processing method of capturing data. On this diagram, it shows a satellite orbiting the Earth's surface, and it's actually getting the reflective energy from the sun. So this is the sun, shining on the Earth's surface is reflected on buildings and houses and the roads and bare earth and grass area, water bodies and forested areas. All of that is reflected, and using specific sensors, particular type sensors that captures ultraviolet, infrared, and other parts of the electromagnetic spectrum, that data is all stored in the captured by the sensors on the satellite and stored and sent to ground receiving stations from the satellite. And the ground receiving station will do the post-processing of the data, remove this, minimize the errors, address the spherical nature of the Earth's surface, and it will prepare maps. All right, or data. It will provide the data for end users to use in their GIS analysis. So this is one example of an imagery, infrared imagery. Another example of a different type of same area but different data being shown. Another data acquisition method is using existing digital database, searching for data online. In today's computer era, there is a large amount of existing data via the internet. Before importing data from other systems, one needs to consider the following factors. What format? Is it a JPEG file, a TIFF? Make sure it's properly georeferenced. Is it a DWG file from AutoCAD? Is it an ArcGIS shapefile? There are many other formats. So make sure that you know the type of format and make sure that your GIS software can import and export in the necessary format in order to do the processing. What is the content? Refers to the theme presented. What sort of information is being presented in the data that you found out or discovered via the internet? What resolution? What's the pixel size of, if it's a raster data set? If it's an image, what's the pixel size? What is the quality? It refers to the effect of errors and inaccuracies of the data set. So a number of considerations, and quite a bit of these you would get in the metadata description if the people that provide, or the organization that provides the data set facilitate who collected any metadata for each data set. This is an example of an existing digital database where, for example, organizations might have data readily available to end users via the internet, or they can create CDs and download their data and send it to users who have made a request. And that data includes, in this particular type of data set, it's a shapefile, it's an ESRI file format. It has its graphic component, which are a set of point, line, and polygons. And each one of these is going to have its associated attribute table. So this imagery shows the spatial data and also inherent or built within the GIS data. It has its attribute tables. Now, the other topic we're going to cover here is GIS data types, and I have categorized them as two areas. Your GIS data must have a basic geodetic framework, and there are different levels in terms of the accuracy of this framework that we would use to record features from the real world. Now, there are different levels of accuracy based upon the scale, and I try to give you some examples of what sort of positional accuracy you get with a typical map scale of, let's say, for example, we have a scale of 1:600. We would get an accuracy in terms of the position. It's going to be 0.5, half a feet. So it's pretty much based upon what your intended application. You try to choose an accuracy is going to be within the specifications as defined by your client. So choose a map accordingly. Other topographic features you want to be included into your geodetic framework is it all depends upon what is the intended application. You might want to put in man-made features or natural features like mountain ranges, rivers, cliffs, etc. Other topographic features include roads, railways, and the list goes on. And again, you don't choose all of them, you don't collect all of them, you only choose the amount of data that's going to be beneficial for your GIS application. Do not put unnecessary data, because you don't want to have a cluttered application, a cluttered map or cluttered application, because if your end users don't use it, then your application is not going to be bringing any benefit to the intended users. Other layers or other data sets you might want to include on your geodetic framework is you can have cadastral features, which is your property boundaries, any easements, land parcels, the type of zones they are in, any area boundary features, things like your city, your district limits, election districts, police boundaries. These can all be looked upon as different data layers in your GIS. Of course, all of them need to be properly georeferenced. When I say properly georeferenced, in order to use the data set, it has to be on a common projection system that all of them are using. You can also include facility features like social facilities, for example, where the playgrounds are, where the open spaces, any common areas being shared in a community, things like that. Natural features like, for example, mountains, any fault lines, rivers, and then another one you can look at is probably socioeconomic zones, where you look at household survey data, income, occupation within a society, etc. This concludes our talk about data in GIS. I would strongly urge you to download the PowerPoint notes page handout, go over the material, make sure you understand it, and we will continue with our next lecture.